Here's the last video for the week 2 agenda. We're going to wrap up our study of how to name and draw chemical formulas for ionic compounds. And we want to focus our attention in this video to a select group of compounds called acids. An acid, by definition, is an ionic compound where the cation is H+. And in this video, we're going to look at 3 different categorizations of acids and the naming rules for each grouping. We're going to look at binary acids, oxoacids, and organic acids. And to begin the video, I'd like you to have your Alchem periodic table of ions handy so that you can see some key features on this table that are going to help you with naming acids as well. I'd like to draw your attention to a box inside the table of complex ions box right here that we will get to when we're looking at the naming rules for oxoacids. And then I'd also like to show you another sort of a little cheat box, if you will, called naming acids here, which will look at the key rules for naming binary, oxo, acids, and organic kind of fall a little bit under the realm of oxoacids as well. So those are 2 key features I want you to be able to refer to as we go through the video. Let's begin by looking at binary acids. We looked at the word binary in previous videos in this week, and we know that binary means 2. Therefore, we would expect that binary acids are those that contain 2 different types of elements. And by definitions, one of those must be H+. Therefore, the other one would be a non-metal on the right side of the periodic table, or more specifically would be an anion of a non-metal found on the right side of the table. And we notice that all of those anions on the right side of the staircase end in IDE when we're referring to their proper names. Let's take a look at some of these acids. If we look at HCl and we come up with its ionic name, we would do as we have all week, and we would name the cation followed by the anion. And so looking on your Alchem table, you discover that H+ would be called hydrogen and Cl would be called chloride. In similar fashion, if we looked at HF, we could come up with an ionic name of hydrogen fluoride. I'm going to skip the next one and go down to the last one for a moment. If we looked at H2S, we could deduce that its name would be hydrogen, followed by the S2- anion, which is called sulfide. Now let's take a moment to look at this one that's HCN. You'll notice that it's not binary and that there are 3 elements in that particular chemical formula. However, we're going to categorize it here with the others because if you look up CN on your Alchem table, you'll discover that its name is cyanide. And we're going to allow it to fit into this grouping of rules because, not because it's binary, but because it shares that IDE ending along with the other anions that we're looking at in this section. So the name of this one would be hydrogen cyanide. Let's see if through a few examples we can look for some patterns between the ionic name and something new called the acid or the classical name. And the acid and classical names are still used on labels, and so it's important that we have an awareness of the relationship between ionic names and acid names. Ionic names act very nicely as a bridge between the chemical formula and the acid name, so it's nice to organize the table in this order. Hydrogen chloride's acid name is hydrochloric acid, an acid that undoubtedly you've heard of in grade 9 and 10 science. Now, if hydrogen chloride is named hydrochloric acid, you might predict then that hydrogen fluoride is named hydrofluoric acid. And in a similar fashion, hydrogen cyanide would be named hydrocyanic acid. And lastly, hydrogen sulfide would be called hydrosulfuric acid. Take a brief moment to note that there's an extra little syllable in here that isn't present over here. Sulfur is one element that we add that extra little syllable in just to make it sound better. So we don't say something like hydrosulfic acid and it kind of gets caught in our throat and we can't make it sound real nice. The only other element that we do that for is phosphorus. And phosphorus in this example would become hydrophosphoric acid. Its ion name would be phosphide if you look it up on that periodic table. So its extra little syllable is OR, whereas here for sulfur it's UR. So I just wanted to plant that seed with you because you will come across it as you practice later. So can we look for a general rule between the relationship of the ionic name with its acid or classical name? This general rule is actually found on the alchem table in this naming acid box right here. It's actually the very first one that's listed. And that rule is as follows. If we have the ionic name, we can say that hydrogen blank-ide, so for example, hydrogen chloride, would become hydrochloric acid. And we can take what's in the blank over here, write it into there, and there's our relationship between the two names for this particular acid. And so those are the rules for binary acids. Let's look at the next grouping of acids. These are called oxoacids. Oxoacids, by definition, of course, must also have H plus in them, but they have oxygen and one other element in them as well. And that oxygen and other element are found or located as a complex ion on your complex ion section on your periodic table. What we're going to do is we're going to build quite a number of rules in this slide right now. And what we're going to do is begin with a complex ion that has a very special ending. We're going to look at ClO3. And if you locate ClO3 in the alchem table, you'll notice that its name is chlorate. So the name of this acid would be hydrogen chlorate. I want to take just a brief moment to tell you that this second letter right here is in fact an L and not an I. And what I do to differentiate between that problem that arises in some type fonts is if I want it to be an I for you, I will always make sure that it's an I that has crisscrosses on the top and the bottom so that there's no confusion between L's and I's. Okay. Let's take a look at the acid name for this. Hydrogen chlorate, you might think might become hydrochloric acid, but of course that's a problem because we've already got that name in the binary acid slide that we looked at previously. So what happens here is we're not going to use that prefix hydro anymore. It's reserved just for binary acids. Instead, we'll just call it chloric acid. And we can see this relationship between ate and ic acid as it pertains to the ionic name and the acid name respectively. Now, let's take a look at what happens if we modify the complex ion slightly. Let's say instead of having ClO3, let's say that we increase the number of oxygens in that complex ion by 1. We would end up with a chemical formula of HClO4 and 1 minus. And notice that the charge on the complex ion has not changed, just simply the number of oxygens has. If we take a look at the name for that complex ion, ClO4, we see that it's similar to ClO3, except that it has a slight change. It has this per beginning to it. And what's really cool here is, again, if you go back to your alchem table, you'll discover in this box right here that one of the first things that listed is that per means add an oxygen to the ate form, or the most common form, of a complex ion. So these rules are not memorizable. They're actually on your periodic table. You just have to know how to use them. Now, if we come up with the acid name for this, in our previous example, hydrogen chlorate became chloric acid. Therefore, hydrogen perchlorate would become perchloric acid. And again, we still have this ate to ic acid relationship going on between the two columns. Let's take a look now at what happens if we reduce the number of oxygens by 1. The chemical formula for the acid would correspondingly be HClO2. And again, a 1 plus and a 1 minus charge would have those acid or those pieces come together in a 1-to-1 ratio. Let's take a look at the ionic name and see how it changes to indicate a reduction of an oxygen. We see that the name of the complex ion now becomes hydrogen chlorite. So ite must mean 1 fewer oxygen than its ate form. And hey, guess what? This rule is also located in this section of your alkane table here as well. Take a moment to note it. It has 1 fewer oxygen than its ate form. So hydrogen chlorite, when it becomes an acid name, changes a little bit in that chlorite becomes chlorus acid. So there's a relationship here between ite and us acid when we're going back and forth between ionic name and the acid or the classical name. Now let's take this just one step further. Let's go to the scenario where we have a reduction of 2 oxygens from the most common 8 form of an ion. And so in this case, we would have HClO, 1 minus. Notice what happens to the name. It goes from being hydrogen chlorite to being hydrogen hypochlorite. The way I like to remember this is that if there are 2 changes or a reduction of 2 oxygens in the complex ion, there are also 2 changes to the name, the ending and the beginning. And hypo is a prefix that you know it means deficient in or a lack of. So let's take a look at how we would go from the ionic name to the acid name. Hydrogen hypochlorite would become hypochlorous acid. So then again, we see this ite to us relationship going on between the 2 columns and just taking the piece across. So we have covered a whole wealth of rules here. We looked at rules that exist going in a vertical fashion in this table, but also in a horizontal fashion in this table as well. And you don't necessarily need to write these down because, again, they're all on your Alchem table. But if you do wish to, you're more than welcome to. It's more important that you know where they're located, but most importantly that you know how to use them. All right, we have an opportunity here for you to practice because these are the rules that students typically get stuck on. We've been doing nomenclature all week and you're tired of it and there's so much stuff to remember, and this is sort of where the wheels tend to fall off the cart a little bit. I want you to pause the video, set up this table. I want you to try to apply the rules that you've just learned to be able to fill in all the cells. Once you've done so, unpause the video and check your results. Okay, here's an opportunity for you to check. And hopefully you've been able to apply the rules both in a horizontal and a vertical fashion in terms of what we practiced on the previous slide. Before we exit the slide though, I'd like to ask you one last question again to make sure you're paying attention at the beginning of the video. What do you notice about the relationship between the ionic name and the acid name with sulfate? Okay, so going across from here to here. And you note that if 8 becomes ic acid, well, let me try that again, that what comes before it should match according to that rule. Well, you notice here that there's sulf, and here there's sulfur. So hydrogen sulfate doesn't become sulfic acid, because again, that's very hard to say. Have an awareness of that extra syllable with sulfur when it's in a complex ion, but also with phosphorus when it's a complex ion. Now you can have some that don't have the sulfur in their name but contain sulfur, so just be aware when you're working with English and you say the word sulfur that it makes more sense to add that extra little syllable. This is different from carbonate because carbon is not one of those elements that you need to worry about adding that extra syllable with. We have one last family that we'd like to go through here to make sure that you've got the basics for everything. The good news is this is a very small family. It's called organic acids, and I just want to plant the seed about organic acids with you. We'll study them in much more depth than for you. These contain oxygen and carbon in a complex ion, but if you look really closely, they all have something structurally in common. They all have what I call Cu in them. Maybe it might be written backwards or forwards, but Cu and Cu. And so there are only 4 complex ions on your Alchem table that we need to worry about in this scenario. If we name this ionically positive part and negative part, first of all, you notice that the positive part is written at the end instead of at the beginning, or it's written right next to one of the O's. And the reason for that is because it is in fact bonded to or attracted to one of those O's. It is not bonded to the carbon in Cu, or any extra carbons might be present as well. So that's just one of the things to be aware of. In 3U, I don't mind if you flip the order around and write H here, for example, in front of this complex ion, which happens to be acetate. That's fine. If you want to be consistent and do positive and negative, go for it. Okay. Now the neat thing again is this ends in 8, so hydrogen blank 8 becomes blank ic acid, so this becomes acetic acid. This one, the H part is hydrogen. The C2O4 or OOCCOO on your Alchem table is called oxalate, and you'll see that that would become oxalic acid. Or benzoate, benzoic, or stearate becomes stearic. And again, you notice that these tend to list the anion first and that they all have Cu in their anion. And that's it for acids.